All right, so this is a quiz I'd given in the past, and it goes over the units of this 1D motion kinematics section, and it also goes over some calculations as well. And usually I give this as a quiz as well, but this year's different, so maybe that's probably not going to happen. But anyways, let's just go through it. And if you want to pause the video and try to write down all the variables and units and signs and definitions, you can do that right now. And then I will give you the answers. So if you want to go ahead and hit pause and do that, go ahead. All right, let's see how you did then. Distance, the variable here, I like to use the letter D. Acceleration. Actually, I'm going to go just straight across here with distance. All right, units here are meters, so we'll use symbol M. A definition, I like to just say how far. How far an object has moved, something along those lines. I don't have very much space here to write, neither do you. And so unless you're doing a separate sheet of paper, then that's a different story. Possible signs, distance is always positive, so just the plus sign. Why is this? Because distance is a scalar. And we talked about that in the notes. All right, acceleration, lowercase a. And the same with distance. Notice we're using a lowercase d. So don't just use, it is important that you don't just use uppercase or whatever you want. Units here, we're going to have meters per second squared. But I kind of don't like always writing that, because a lot of times kids don't know what that means. So remember that when we write that, what we're really saying is meters per second, right? That's really how it's how much your meters per second change, or your speed or velocity every second. It's how quickly your velocity changes, how quickly you slam on the brakes, how quickly you press the brake lightly, how quickly you hit the gas pedal. That's what we're saying here. So it's how much you change your meters per second every second. And so we like to mathematically converge those two, right, and get meters per second squared. All right. So we write meters per second squared, but it means meters per second per second. Okay. Definition. How quickly your velocity changes is probably a good way to write it. Signs here. This is a vector, so it can be positive or negative. All right, an acceleration's sign I'll talk about in a lecture here. It can be kind of tricky. Yeah, so I'll go into that at another point. Because you have negative acceleration or deceleration, and I just want to mention that in a different lecture. All right, velocity, just the symbol V. Notice we have that little curl in front of the V. Units are meters per second. And this is how your speed, I'm going to say speed in a direction. Actually, I don't even want to say that, because I think that's confusing, because we know that velocity isn't the same as speed. Instead, oh, dang. You know what? I think, even for the last one, I think previous years, what I had always done here, let me erase this one too. So I'm thinking previous years, what I did here for the definitions of acceleration and velocity is I just wrote formulas. So this is the formula here is change in velocity over time. And the formula here is change in position over time. And I like doing that better. So you can see then acceleration is how quickly your velocity changes per unit of time, and velocity is how quickly your displacement changes per unit of time. All right, I like that a little better. Possible signs here, positive or negative, because displacement is a vector and therefore velocity is a vector. So positive or negative velocity indicates the direction you're traveling. Okay, so displacement, delta x, units here are just meters. Definition, change in position. Could we just write the formula here for this? Yeah, but I think it's better to write it out in words for this one. Sign, positive or negative, because it's a vector as well. Position, just represented by the variable x. Units are meters. Definition, location. Possible signs, position can be positive or negative. It could also be 0. And that's true of any of these. They could all be 0. Finally, time, t, units, seconds. Definition, how long it takes. Possible signs, time is only positive. The arrow of time, it only moves forward in one direction. So we can call time a scalar. Position. Can position be a vector? Yeah, I mean, it can have a sign. It can point in three-dimensional space. So, yeah, I think I like calling that a vector. But does position point? It's kind of just a location relative to another location, which gives it its sign. I'm going to go with calling it a vector right now, although I'm going to have to come back to that one and think about that. Okay. All right, so here we have a dog walking 25 meters east, 45 meters west, then 22 meters east in 70 seconds. So, with a problem like this, and I think I have some room below here, so I'm just going to use this room. I'm going to draw this out. First thing I'm going to start with is a number line. Draw position 0 in the middle. And then start by saying the dog walks 25 meters east. Okay, well, which way is east? We'll call right, which is the positive side, east. And we'll call west, the negative side. All right, and so the dog's going to walk 25 meters east. All right, so it's going to get to position 25. Right, this is 0 meters. And so let me think of how I want to write this. This is going to be x initial. I'm just going to call it x0 or x naught. This is going to be x1. And this dog is going to walk. Yeah, I like that. And then the dog is going to walk 45 meters west, so it'll take 25 to get back, and then 20 more. So we're saying about right here, which is going to be at position negative. Whoops. Dang it. Negative 20. All right, so we're saying with that next move, the dog goes here. So so we're seeing, okay, I'm just going to leave those arrows there right now. And this is going to be position x2. And then finally, the dog walks 22 meters east. So if it's at negative 20 and walks 22 meters east, then its final position, or what we're calling position 3, is going to be positive 2 meters. Okay. So it has one last move here, doing this. And so, okay. So the first question is, how far does the dog walk? Well, we can see from the orange arrows, the dog walks 25 meters there. The dog then walks 45 west, so 45 meters there. And then it walks 22 meters east, so 22 right there. So we can see for part A then, we can see the calculation is going to be 25 meters plus 45 meters plus 22 meters. And we don't care or give a rip which direction the dog's going in. So it looks like we got, what is that, 47 and 45, 92? All right, part B. Let me switch colors now. Part B. Okay. What is his final displacement? All right, so displacement is the variable delta x. And delta x is equal to xf minus xi. So what is the final position? Well, that would be, why is this not wanting to write here? Oh, my bad. That would be x3 in the initial position, x naught. So we just assumed, and I didn't really talk about this, but we just assumed it started at 0, right? And we can always say that. Even though the problem doesn't say that, we can always assume the initial position is 0 if we want. What if you assume the initial position was 100? Would that change anything? Well, it would change your locations, but it wouldn't change the answer to any of these questions. So you're free to start the dog at position 100 if you like. And that's fine. It won't. All your answers will still be right. X3 is positive 2. And I don't have to write that positive sign. I'm not going to. That's just going to make it a little more confusing. So we can say 2 meters minus 0 meters and get 2 meters for our answer. Notice in the positive direction. So our displacement here is positive 2 meters, or you could have said 2 meters to the right, because that's what that positive sign means, and we have to get used to that coming from math class where maybe we had positives and negatives but they never had any meaning. Now they do. All right, what is the average velocity and speed? So C is average velocity, so V average, or just V, I'm just going to call it V. Why is it average and not instantaneous? I think we've had this lecture before. If it's average velocity, it's over a large chunk of time. And if it's instantaneous, it's over the smallest chunk of time that we can get, or that we can think of. So, yeah, that's the difference there. So we're saying average velocity, which is going to be over this entire time period. So we're going to have V equals delta x over t. You don't have to write the average sign next to the V. It's okay. The fact that it's an average, like I said, shows up in the fact that this is over 70 seconds. So V then is equal to the displacement, which is positive 2 meters, divided by the total time, which is 70 seconds. I'm going to need a calculator for that because that is going to be a very small number. All right, I am getting 0.0285, 0.0286. I'm going to go with 0.0286. Oops. 0.0286 meters per second. All right, and once again, that is positive or to the right because our displacement is positive or to the right. All right, and then part D asks for speed. So even though like the net movement of this dog that's going a bunch of different directions is in the positive direction, right, and has a positive velocity, albeit a very small one, the dog is actually moving a speed that's much faster, right? And we can see that because the dog is going to be moving in the negative direction sometimes. So we can see that reflected in the speed. And the velocity, we don't really see that, but it's factored in, right? It's factored in because that's why the velocity is so small. The dog's speed is its distance, which was 92 meters, divided by that time, which is 70 seconds. Once again, I'm going to type this in the calculator and get about 1.286. So a much larger speed, and speed is always positive, and there you have it. All right, hopefully that's making sense. I like those questions, but always start with a number line. I really think that helps students in the past, and then go from there and answer the questions. All right, next question. A car drives 45 miles per hour in 175 minutes. How far does the car move in miles? So when it's saying how far, it's asking for distance. And I just wanted to point that out because of the how far. So a lot of times in my class, it's tough for students to start the problems, meaning the math isn't terrible, but the math isn't terrible, but it's tough for students to start. So 45 miles per hour in 175 minutes. So right away, I'm just going to jot some of this down. I'm also going to label what the heck this is, and because I'm gathering up the variables is really what I'm doing, right? Okay. So this question is number 8. All right. So you can see there's 3 things. One we don't know. So this is fairly simple algebra. Speed equals d over t. I go find my formula, plug in what I don't know. But I notice here that I'm not going to be solving for speed, so I technically do need to rearrange this formula. So I'm going to do it right now before I plug numbers in. When I was in school, I used to always plug numbers in first because I like the numbers, but the teachers would always hold off on doing that because you can see relationships in the variables that you can't see when you plug numbers in because the numbers start to connect together, right? So it seems easier as a student, but it's more elegant this way because now you can see relationships that maybe you wouldn't see when you just keep the variables there. So we see that distance is equal to speed times time. All right, the only problem here, and this should be an alarm bell going off, is this, right? These don't match, and this is a problem. You can't have 2 units of time. Now you might say, well, I thought this was physics class and Mr. Rodriguez is always saying we're using seconds. Now, that is true, that a lot of times in this class, we're going to default to seconds, and we're going to have to kick these units into seconds. But for this problem, it makes sense just to leave it in hours or in minutes and work from there. It's just as valuable. It's just as useful. There's no real need here to switch it into seconds. So and if you can't see that, well, I think it'll make more sense the longer you're in this class and the more of these problems we do. So what should we do here? Well, we could switch the hours into minutes. So we are moving at 45 miles per 60 minutes. That's probably the easiest way. So what I'm saying here is our speed, I don't know why I'm writing this here. It's just going to be in the way. Our speed is equal to 45 miles per 1 hour, right? And I'm going to now write that. I'm just going to, well, actually, I'll just do some dimensional analysis or conversion factors. It'll make it much easier rather than me showing you some different way. So I know that 1 hour is equal to 60 minutes. Cancel. And multiply the top across, multiply the bottom across, then divide. So we're going to get 45 miles per 60 minutes. Do the math there. You should be able to do that in your head. Both divisible by 15. Three miles per 4 minutes. Interesting. So when you travel 45 miles per hour, 45 miles in 1 hour, you're going 3 miles every 4 minutes. Or you could say 0.75 miles per 1 minute. That would also work. All right, so either way, I'm going to keep it as 3 miles per 4 minutes. That sounds kind of neat. All right, so distance is equal to 3 miles every 4 minutes divided or times by this time, 175 minutes. And that's over 1. Okay, so now we can cancel minutes. And we're left with 3 times miles times 175 divided by 4. Okay, so now we get the calculator, crunch that down. $131.25 miles. All right, done with that. Let's go to the next question. Number 9, car's velocity decreases by 32 meters per second in 8 seconds. What is its average acceleration? All right, this is interesting because when we get our acceleration formula, this is for number 9. Acceleration is equal to delta V over t, and a lot of times to use this we split it into VF minus VI over t. So when a lot of students look at this, they're like, well, which one's 32, right? It decreases by 32 meters per second. And the way to solve this is to not split it up yet. So even though most times we're going to split it up like this, and that's going to be the best way through, this time it's actually better to use this top formula right here. So what we're going to do then is just realize that a decrease is a change, and because it decreased, it doesn't matter what it decreased from. It could have been 100 to 68, right? So 68 could be final, and 100 could be initial, and that's fine. But I'm just going to go with the fact that the decrease is the change, negative 32 meters per second, and that this was accomplished in 8 seconds. So it's going to look something like that. So I just went from that formula to there. Right there is what I did. All right, so my acceleration is negative 4 meters per second squared. And remember that this is the same, whoops, negative sign wasn't there, same as 4 meters per second squared to the left. If left is negative, assuming that's the case, right? Assuming left is negative. So it might not be, right? So you could have said 4 meters per second squared in the negative direction. Remember, this also could have been written as acceleration equals negative 4 meters per second. So that the car, or whatever this was, its velocity decreased by 4 meters per second, or the car's velocity increased by 4 meters per second in the negative direction. That's interesting to think about. And in the acceleration, how if you have a negative acceleration, you either decreased your acceleration in the positive direction or increased your acceleration in the negative direction. And they're both the same. They both mean the same thing. And that's why I didn't talk about it above. Try and go over that in the lecture if I didn't already. But yeah, that's kind of tricky to think about. All right. So a negative acceleration means you decreased your velocity in the positive direction or you increased your velocity in the negative direction. So decelerating in the positive direction is the same as accelerating in the negative direction. Okay. Number 10. A car is capable of accelerating at 20 meters per second squared if it starts from rest. How fast will it be moving after 3 seconds? Okay, so what do we know here? Well, we know acceleration. Rest, that means it stopped. So this is going to be VI, and VI is going to equal 0 meters per second. And we want to know how fast at some later time. So we want to know VF, and then the later time is 3 seconds. So you can see we can solve this fairly easily now that we've interpreted the problem. All right, so let's go down here, write our formula. What number is this, 10? All right, so for number 10, we're just going to go ahead and write our formula. Acceleration equals delta V over T. I'm going to go ahead and split that top part into VF minus VI over T. And then I'm going to start plugging numbers in. Whoops, I think I know acceleration. Or am I looking for acceleration? Dang, I already forgot. Acceleration's 20. VI is 0. Time is 3 seconds. Okay, so we do a little math there, or I'll just rewrite it so it looks a little bit easier. So it's easier to look at. Okay, so here, sometimes I don't write units just to make this look easier. Because really, ultimately, like this looks like maybe you cross multiply or something difficult. But really, this is the same in math class as just seeing this. And I think if I gave that problem to everybody would be like, oh yeah, what's your next step? Multiply both sides by 3. And that is the same thing we're going to do in this class here or with this problem. However, the units go for the ride too. So when I do that, I can cancel the 3 and I can cancel the seconds. And just like here, I can cancel one of the seconds. So long story short, you end up getting 3 times 20 times 20 meters. I guess I was gonna write it as 20 times meters. I'm not gonna make this tougher than it needs to be. Divided by seconds is equal to VF. And check that out, right? This is the units of velocity. So we can go ahead and rewrite that now as 60 meters per second. Velocity has a direction, right? Positive. So you could say 60 meters per second to the right. Assuming that right is the positive direction. Something you would have to declare at the beginning of the problem, or it'd have to be stated at some point by the problem. All right, That's it. I think that's all the problems. So hopefully that helps, and the units are going to start making sense, and this new terminology is going to start making sense, because I know that that's a lot for students, like knowing, first of all, understanding what all these variables mean, and then understanding what units go with them, and then having an idea of what formulas and what they mean. Also, understanding that when you get a problem in my class, a lot of times it's going to be written like this, and that means that you're going to have to interpret it, right? You're going to have to dig the variables out and find the equation. Now, that's a pretty straightforward way to get through this class. An even higher level of thinking to get through this class would be, well, I have a question about a car. Do I solve it with kinematics, like in this chapter, or do I solve it with momentum or energy or forces? And that's the next step to move on to. So, because it's pretty, it's pretty useful to just hunt for an equation, plug in the variables you need, and solve for the one that's left over. But it's not a real higher end way of thinking, right? An even more universal way of thinking would be like, I saw this balloon rising through the air the other day outside, and I wanted to figure out what its speed was. Is kinematics the best way to do it? Or maybe is it energy, or is it forces? Or is it something to do with pressure? So that's kind of the next step, right? Moving on to thinking about concepts and how they relate to something you see, right? Oh, I saw this car that was that had this had a spoiler on it, right? And I was like wondering, well, why? Why does the car have a spoiler? What's that doing? And then trying to figure out what is the concept there that the spoiler is taking advantage of, other than just to look cool, right? All right, so anyways, that's it. Have a good day. I hope this helped.